Hello everyone. In this lecture, we will introduce the circuit model of the MOSFET. You've been familiar with the MOSFET since in lecture 9 and the second lecture of the simulation. We've known some external characteristics of the MOSFET and gotten some characteristic curves by the simulation. In this lecture, we will introduce how to build the circuit model of the MOSFET based on its external characteristics. Firstly, let's intuitively learn some applications of the MOSFET in real circuits. This is a CPU. There are hundreds of millions of transistors in one CPU. Most of them are MOSFETs. This is the application of the MOSFET in an amplifier of the headset. This is the application of the MOSFET in the peripheral power supply circuit of the CPU. In the power system, the MOSFET is also widely utilized. Although all of them are called MOSFETs, in fact, when applied in different situations, they are quite different in many aspects. Firstly, intuitively, MOSFETs in the CPU and the power MOSFET have huge difference in size. The size of the MOSFETs in the CPU is with the order of magnitude of nanometer, while the size of the power MOSFET is much bigger, which can be 10 centimeters or more. Secondly, their functions are different in various applications. The MOSFETs in the power system and the power supply circuit for the CPU are basically used as electronic switches, while the MOSFETs in the amplifier of headset are used as an analog signal amplifier. We will understand this point after learning the applications of the MOSFET in the digital circuits and lecture 45 about the MOSFET's applications as a small signal amplifier. Thirdly, the internal structure of these MOSFETs also have differences. MOSFETs applied in the low power cases have horizontal conduction channel between D and S, while the power MOSFETs applied in the power system have vertical conduction channel between D and S, which can raise their voltage level. Okay, after learning some applications of the MOSFET, we will introduce MOSFET's operating principles. You can learn the detailed working of the MOSFET in the course of microelectronic circuits. In our course, instead of the detailed explanations, we just use two animations to help you for better intuitive understanding of how the MOSFET works on Earth and how the conduction channel between its D and S is formed. Firstly, let's see how the conduction channel is formed. When the power source is only connected between G and S instead of D and S. With the increase of the UGS, you will see the forming of the conduction channel between D and S, in which the current flows. Since there's no voltage between D and S, the channel has constant width. With the decrease of UGS, the channel is cut off. Next, let's see the change of the conductance channel's form when the power sources are connected between G and S, D and S both. You can see now the channel is a wedge shape, which means the two sides don't have the same width. Let's see how the channel changes when we change the value of UDS and keep the value of UGS constant. With the increase of UDS, channel near D side is cut off. Firstly, the cutting off region becomes larger and larger with a gradually increase of UDS. Reversely, with the decrease of UDS, the conduction channel will be formed again. Anyway, the channel always has a wedge shape with different widths on two sides in the process. Similar to the op-amp, you are not required To grasp the detailed operation principles inside the MOSFET in this course, you are only required to grasp its external characteristics and build its circuit model based on these characteristics, which means to represent the MOSFET's external characteristics in the corresponding operating conditions with some simple elements such as resistors, controlled sources, and so on. This is a common circuit of the MOSFET application. We can see G and S terminals form a port, and the D and S terminals form another port. There are four physical quantities on the two ports, which are UGS, IGS, IDS, and UDS. So there are four combinations of them to represent its external characteristics. According to what we've learned before, there is a layer of the oxide between MOSFET's gate terminal and the source or drain terminal, which allows no current to flow in through. In other words, IDS is always zero. So we don't need to plot these two curves. We will focus on the relationships between UGS and IDS and UDS and IDS. Firstly, we will learn the relationship between UGS and IDS. You've seen the curve before by the simulation. UGS and IDS don't represent the voltage and the current of the same port, so it's called a transfer characteristic curve. In this course, we find when UGS is less than some value, IDS is zero. The region is called the cutoff region. When UGS is larger than some value, IDS increases gradually. This value is called the voltage control threshold of turning on, marked as UT. When UGS is less than UT, MOSFET is turned off. When UGS is larger than UT, the MOSFET is turned on. And the current can flow from D to S. You can review the second lecture of the simulation for better understanding. Next, we want to know what characteristics MOSFET does the curve represent when IDS is larger than zero and the MOSFET is turned on. So we focus on the relationship between UDS and IDS. UDS and IDS represent the voltage and the current of the same port, that is the output port, so their relationship is called the output characteristic. We get the characteristic curve between UDS and IDS in the second lecture of the simulation. Obviously, UGS has impact on the characteristic. The curves are corresponding to different UGS. The bottom curve means when UGS is less than UT, the MOSFET is turned off. So IDS is always zero. You may pick out one of the curves and analyze it, which is corresponding to UGS being equal to 5 volts. It can be represented by a polyline for approximation. According to the previous lectures, we've known the straight line crossing the origin point, that is the first part of the polyline, can be represented by a resistor. It's called the controlled resistor, since the slope of the curve, which also means the conductance, is controlled by UGS. IDS is constant in the above part, so it represents a characteristic of a current source. It's called the saturation region, or the constant current region. The region represents a controlled resistor is called the resistive region. According to the previous lectures and these simulation curves, we can see UGS has a significant impact on the output characteristic curve. Whether the value of the controlled current source or the controlled resistance are both influenced by UGS.